My name is Sam Goldsmith, and I did my project on shadow bands. On August 21st, I decided to drive down from Champaign to Carbondale, Illinois to witness the total solar eclipse. This was the scene directly after the total eclipse. It's very subtle, but on the parking lot pavement, you can notice bands of light traveling across the ground. Prior to taking ME 498, this phenomenon was very confusing, and I did not understand what was causing it. Here it is again with a black and white filter. First literature on shadow bands actually appears in the 9th century by an Icelandic poet. Later in 1842, an English astronomer noted that the bands were so striking that children were running after them trying to catch the light. As you can see in this photo, the phenomenon looks similar to the light reflecting off the bottom of a pool. Shadow bands are extremely difficult to study as they only occur in the seconds directly before and after a total solar eclipse under turbulent atmospheric conditions. In order to fully understand the phenomenon, we will explore two optical concepts: collimation and refraction. Let's begin by discussing collimation. One of the cool astronomical coincidences of living on the Earth is that from the surface of the Earth, the Sun is roughly the same diameter as the Moon. During a total solar eclipse, the Moon traverses directly in front of the Sun. As the Moon crosses in front of the Sun, it increasingly collimates the light coming from the Sun. In the final seconds before totality, the light passing through the Moon becomes a thin crescent and finally a single point of light. It's during these final minutes that the light from the Sun is collimated enough to produce shadow bands. After totality, the same phenomenon occurs as a small sliver of light begins to peek through the opposite side of the Moon. The next optical concept that is necessary for understanding shadow bands is refraction. As we touched on earlier, there must be sufficient atmospheric turbulence to maximize the effects of shadow bands. Let's start off by drawing the Sun and our human observers on Earth. Earth's atmosphere is composed of different layers of air that vary in temperature and turbulence. As light travels from the Sun through these layers, it is refracted at various angles depending on the density of the air. When the light from the Sun is collimated during a solar eclipse, the bands of light emitted from the thin crescent are passed through these atmospheric layers, which create the moving patterns of light bands on the ground. This phenomenon is called stellar scintillation and is commonly observed when we see stars twinkling. One of the cool things about this phenomenon is that because it's so simple, it can easily be recreated using household items. For example, if we use a flashlight to represent the Sun, and we cover that flashlight with a small pinhole opening, we can simulate the collimated light coming from the Sun right before a total solar eclipse. To generate turbulent air, we can simply light a candle. The setup is simple. Collimated light shines through the pinhole over the turbulent air from the candle and reflects off of a piece of grid paper taped on the wall. The result is very faint shadow bands. I had a really hard time picking them up in the dark with an iPhone camera, but they are indeed there. I want to thank you for taking the time to watch my video. I hope you now have a better understanding of how shadow bands work. And there's another eclipse coming up on April 8th, 2024. So make sure to mark your calendars and check out some shadow bands.